embarrass them as they come in. So today we don't have a whole lot of big picture stuff to do. It's a lot of little things. I have a lot of things to complete this basic section. But first let's just take a big picture moment and think about what we've done. So basically our fundamental experimental fact that we're doing is that we have quanta with energies h bar omega, where omega is the frequency. And that's true in the end, whether they're fermions or bosons, it's massless or massive fields. That's always the case. And our pathway through it was that we used p's with q's, or q's with p's, sorry, that's the usual way you do it. And we turned that into the commutation rule for a field is IH bar delta 3 of x minus x prime. So we turn that into the commutation rule for the fields, and we turn that then into the commutation rule for creation and annihilation operators. And that's 2 pi, I think I have h bars in there in my convention, cubed delta 3 of p minus p prime. And that, we turn that finally into the Hamiltonian is the integral d3p, 2 pi h bar cubed, h bar omega of p, a dagger of p, a of p, or more compactly, sum over s h bar omega s, a dagger s, a s. So yeah, we can use either the discrete notation or the continuum notation, and these just tell you how these things work. Okay. But so that's what we did. That was our pathway, our big picture. But we could have reversed it. So you could have reversed it. And generally, when I teach second quantization in the quantum mechanics course, I actually do it the reverse way. You start with quanta, and then that's the Hamiltonian. Hamiltonian is equal to h bar omega a dagger a, and you get backwards. In this case, we would have gotten back to, a dagger, and from there we could get to phi and pi. I'm actually going to, my very next little bit, so one of the things I said to start the class was that this is a class of a lot of little bits tying things together, completing things. This is the only big picture stuff. But my next little bit is going to take this last step, knowing A and A dagger and going to the commutation rules. So we could have worked the reverse way, but the logic hangs together. And in the end, the A's and A daggers become bookkeeping devices. Okay, everybody for whom English is not a foreign language understands the word bookkeeping when I say that. Bookkeeping is what an accountant does. It keeps track of all the numbers and adds them all up. In this case, the bookkeeping means keeping track of what states turn into what states, just what goes on there. So as an example, if we took incoming states P1, P2, outgoing states P3, P4, and we put 4 fields in between there. So this is a matrix element we're going to encounter later on. Some of these fields here have creation operators, and some of them have annihilation operators. So with some combinatoric factor, which we will call out later, this can annihilate the state P1 from an annihilation operator, annihilate the state P2, create the state P3 and P4. And so that matrix element gets, in the end, represented by a picture, which is P1 in, P2 in, P3 out, P4 out. It's a scattering picture. So if something comes in, pops out in different momentum states. So this quantization will do that. That's where we're headed. Okay, questions about big picture stuff? All right. If no big picture stuff, let's do some small stuff. So this little thing I'm going to do now is inverting. Inverting the fields to get creation operators. And the logic here is I want you to first recall quantum mechanics. Okay, where when we introduce creation and annihilation operators in quantum mechanics, we take x is square root of h bar over 2 omega a plus a dagger. P is minus I squared of h bar omega over 2 a minus a dagger. Okay, and the inverse of that is a is the square root of omega over 2 h bar x plus I p over omega, and a dagger is square root of omega over 2 h bar x minus I p over omega. Okay, and the latter a with a dagger, then so if I take those two, that turns into 1 using the commutation rules for x and p. So let's not forget the vector. Okay, so if you use the commutation rules for x and p, you get a dagger is 1, and that gives you this whole algebra that uses for the harmonic oscillator, creation and annihilation operators. Okay, well, you can sort of see the analogy here. Up to some normalization, phi, which was sort of like x, was a e to the I omega t, and a dagger e to the minus I omega t. And p, which was the time derivative of that, then went like a minus a dagger. So we saw the same things for phi and pi. I just want to do now the inverses. How do you get those? I probably won't do it too much algebra associated with this, but for fields, let me do it. A of k, or A of p, well, I'll let you do A of k, that's what I have here as my notes, is omega over 2 h bar integral d3 x e to the I omega k of t minus k dot x of phi of x and t plus I over omega k pi of x and t. Okay, so let's just look at that. This is like x plus I p over omega, but it's phi plus I pi over omega. Okay. And the prefactor is actually exactly the same. And then there's this little projection operator that projects out of all of these. It just projects out the one you want. And so that turns out to be the generalization. So we now substitute in for this phi of x and t is, the integral d3k, blah, 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 a dagger, blah, blah, blah. Okay, all that stuff from before. I guess I won't. This is the place where I'm going to skip all the algebra. But I'll show you one intermediate step. It's sitting here. There's some normalization factors, all that sort of stuff. Okay, but you see you're going to have 4 terms come out. There's an A from here, an A from there, an A dagger from here, and A dagger from there. You also get the following. You get a, so let's actually, in my notation, if you make that a K prime, so I'm integrating over, that's K prime, that little squiggle. Okay. I have an e to the I k prime dot x here, and e to the I k dot x there, an integral d3x there. There's going to be a delta function come out. K is equal to k prime, or minus k prime, depending on which of these it is. And so the d3k's, the d3x's give us a delta function, which cancels the d3k integration. See if we can do all these things in our head. We end up with the following. There's, it ends up, all the normalizations work out just right. So for this guy, we plug in 1 over v squared phi dot. And all the normalizations work out right, so I get a of k plus a of k. So the first one came from phi, the second one came from pi. And then the next piece is e to the I 2 omega t, a dagger of minus k minus a dagger of minus k. Okay, the first one came from phi and the second one came from pi. Okay, and there's a 1/2 out in front, of course, or else it's not going to work. I end up with just a dagger of k. These two guys cancel, so the a daggers cancel between phi and pi. The a's add between phi and pi, and the answer works. Okay, you can sort of see by construction that you can always do that. This just happens to be it, the piece that you get up there. Okay. Have I hand waved that too much, or can you see how it's going to work out? I have all the details here. I can go through it in as much gory detail as you choose. You're okay on it? Okay, but the interesting thing is, just logically, it looks just the same as above, and in a sense, it is the same as above. Okay. Then here's the interesting thing that I find that happens is that when I take a of k with a dagger of k prime, well, we've got a bunch of stuff here. Again, I'll try to be a little bit cryptic. So there's normalization factors, then this is n and n prime, integral d3x, e to the I stuff, integral d3x prime, e to the I stuff prime. And I end up then with terms that look like phi plus I omega pi commuted with phi minus I omega pi. Okay, this guy's prime, that's x prime. Okay. But these guys, phi commutes with phi, but phi does not commute with pi prime. So these guys equal then this 2 pi delta 3 of k minus k prime automatically. So the pi commutators here this gives me a delta 3 of x minus x prime. So out of this guy comes delta 3 x minus x prime. There's a remaining integration here, e to the I k dot x, e to the I k dot x, k prime dot x, because x is x prime. That gives me the delta function, and it all works out. So that the lesson here is that the phi pi commutator implies the a dagger commutator. It may have looked like that was some arbitrary choice that we made along the way, but it's not an arbitrary choice, it's a required choice. So that all this hangs together beautifully. Okay, all these look like formal manipulations, but they're all driven by the fact that we observe quanta with h bar omega, and we count the quanta by this number operator, and then everything else follows. Okay, so questions? Okay, if there's no questions, I want to do conservation of energy next little bit. Okay. We also derived that the Hamiltonian is the integral d3x pi phi dot minus the Lagrangian, which, just to be clear, it depends on phi, in principle phi dot, and gradient of phi. Okay? It doesn't explicitly depend on time, at least in this formulation. Okay? And pi was the derivative of the Lagrangian density with respect to phi dot. Okay. So what I'd like to do is show that this definition is automatically conserved. It's actually, I'm doing this in more generality than that string. I mean, in the way we did the string, we solved the Hamiltonian. We saw that in the end there was no time dependence, even though these fields contain time variables. The Hamiltonian came out with no time dependence. It was just h bar omega a dagger a. Okay. This is a little more formal proof now. I've got this general Lagrangian here, where without any specific form of it, I'm going to prove that there's energy conservation. And I'll also get out the momentum operator out of this from the flow of energy. So there's my goal. Okay, so watch. Here we go. We want to take, let's leave it up so you can see it there, dh dt. Is that anything? Okay. Okay, well, let's, the integral d3x. All right, so first thing I do is I take the derivative of pi, the time derivative of pi. I take d by dt of dl d phi dot multiplied by phi dot. Next thing I take is, here's pi again. Take the d by dt of phi dot. So that's phi double dot, clearly. Okay, and then I take the time derivative of the Lagrange density, so d by dt of L, which is a function of phi dot, del phi. Okay, let's not write the first stuff over. This then is, that minus I'll just write. You use the chain rule. It's dl d phi times phi dot, right? So dl d phi, then d phi dt. But it could also depend on phi dot. So I do, then it's the dl d phi dot dt, so phi double dot. And plus the partial with respect to del phi of d by dt of del phi. Okay. So chain rule says any time dependence here is either from there's the chain rule. You know the chain rule, right? Okay, at this stage we see one nice thing. This term and that term cancel, so the phi double dot terms cancel. So okay, and this term here I'm going to integrate by parts. Okay, we're integrating over x only here, no t integration. But so I can take the derivative operator here and put it on the other side. So I integrate by parts. The derivative then acts on this term, and I've still got d by dt on phi, so just phi dot sits there. Okay. Now, most often we throw away the surface term, and I'll do that in the end. But actually, I'm going to keep it here because that gives me something else also. So let's do this. So I keep it. Let me first write out the terms that are not the surface terms. So it's integral d3x. Well, the first term I have there is we will see that everything comes out proportional to phi dot, so let's just pull that out. The first term is d by dt, dl, d phi dot. The next term I'm going to write here is the result of integrating this by parts. So there'll still be a phi dot. D by dt of phi is still there. But this derivative now goes over onto this side, changes that to a plus sign because I'm integrating by parts. So it becomes plus del dl d del phi. And then the last piece is unchanged. It's minus dl d phi. Okay, so that was that. And then the surface term is the following. The surface is an area out at infinity, and the piece is delta L d del phi times phi dot. Okay. So if you remember from E and M the way the surface term looks, it's the area dotted into this guy, and then here d phi dt still sits unchanged. Okay? People comfortable with that? Okay, so if we take the surface at infinity, and have the fields vanish there. Okay, so we're just talking about integrating over all space and looking at fields that live somewhere in space. Okay. Okay. Then the surface term is 0, and you recognize that first term there. The first term is the Euler-Lagrange equations for the field. Does everyone remember them? They're from the earlier class. This was the Euler-Lagrange equations, and the Euler-Lagrange equations then say that dH dt is 0, so the energy is conserved. Okay. This is the same thing that happens in classical mechanics. That's why you define the Hamiltonian. The Euler-Lagrange equations are equivalent to energy conservation if the Hamiltonian doesn't have explicit time dependence. So no, it means that in this case, it only depends on time through the fields phi and their derivatives. Okay. So again, like classical mechanics. But there's also extra information here. If you take a finite surface then dH dt is given by the flow of energy across the surface. Okay? And that's what that second term is there. If we define, I'll call it script P, is the variation of Lagrangian in respect to del phi times phi dot. And that's something that gives us the flow of energy. Okay. Which, up to factors of c, and the quantum field theory doesn't have a general name for this except for momentum density. Okay. Now, it probably should be momentum density divided by c squared or some crazy thing like that. But we're soon going to set c is equal to 1, and we'll forget about that. At least I don't know where the c's go. There's no other name for it. It's the momentum density. It tells us how the energy flows. Okay. So my comment on c squared is, that if the energy non-relativistically starts like mc squared, the momentum goes like mv. That's the flow. That's the flow of energy. Just p is mv, but there's some factor of c squared. This is probably that guy's p over c squared or something like that. I'll show you some more about it. Okay, So let me just put here the Hamiltonian density. This was the Hamiltonian density was dl d phi dot times phi dot minus the Lagrangian. And this pair then gives us the energy density and the momentum density in field theory. There's a differential conservation law. If I take the partial of h with respect to t plus del dot this script, that's supposed to be a p, okay, that's equal to 0. And again, I have all the algebra here for working it out. And I guess actually, if we're fussy math people, it's really d by dt, because it's really, you have to take the partial with respect to phi times phi dot, etc. Okay. Actually, so maybe, given the looks I'm getting, maybe I should show you a little bit of these things. Okay, so this is d by dt of the partial of L with respect to phi dot minus L plus del times the partial of the Lagrangian with respect to del phi times phi dot. Okay, and the way the proof goes, again, it's sort of like what I just did, so I won't do everything. You know, you act on these two terms here, and you collect terms, and this guy gets expanded as dl d phi dot plus dl d phi dot phi double dot l d grad phi get phi dot, no, yeah, yes, etc. So and you just combine terms and it all adds up to 0. Okay. Again, I don't know how much we want to do. I could do more. But it's just using the chain rule a bunch of times, and all those terms cancel, just like it happened up above. Okay. And this guy is like our the usual conservation of charge rule. So this is a typical conservation law. You know, you have d rho dt plus del dot j equals 0. When you see this in E and M, that's the charge density. Here it's the energy density. And J is the flow of charge, or in our case, energy. So these things all tie together. There's a differential law that goes with them. And moreover, if I take the total momentum okay, so let's take, let me call it capital P total, I'll put a little bar underneath it, is integral d3x, well, so I've got dl d del phi times phi dot. If I plug this in for my previous solution, so our previous case, or phonons, okay, this turns into integral d3x. The derivative of Lagrangian with respect to del phi is just del phi back again. D by dt of phi. Okay. And now I can calculate that. So I now plug in phi is integral d3k e to the I omega t minus k dot x a, etc. And so you've got d3k, a d3k prime from the other one, a gradient that brings down a k, and a d by dt that brings down an omega. The d3x gives you delta functions. Okay. The delta functions kill one of the d3k integrations. We end up with, here's an intermediate step. Let me just give you the intermediate step. Integral d3 p over 2 pi cubed 1 over 2 omega times p, a of p, a dagger of p, minus a dagger of p, a of p. I know, a plus there, that's a plus. But minus comes here. That becomes a plus 2, actually. Plus there, too. E to the 2I omega t, a dagger of p, a dagger of minus p, plus e to the minus 2I omega t, a of p, a minus p. Okay. So you can sort of see a bunch of stuff here. The del phi gives me a p because I bring down a p. The d by dt brings down an omega, so there's the omega. This was from the normalization, and I have to say that I probably have h bars set equal to 1 in this formula here. So that's my next step is going to be to get rid of these things because I have no idea where they go. But I actually think my h bars are actually okay. Actually, I think there's actually no h bars missing here. Okay. Does anyone want to discuss why you get these terms here? These ones are, the a from this, a from one of them, a from dagger from the other. The ones that have a's and a's come with the same signs and omegas. So it's either the minus I omega t a e to the minus I omega t a from the second term, so that's why there's a 2 omega t here. Okay, I never really know how much people follow these things as I'm doing these. You have to ask if you need it. Okay. But what it is from here to here, it's just plugging in and doing delta functions to get that. There's a trick now at this stage that is slightly different. These terms disappear, and they disappear because the integration over p is an odd function, and this is a of p, a dagger of p, a dagger of minus p. So this is an even function. Omega is invariant under p goes to minus p. Those omegas canceled, but that p is odd under p goes to minus p. So the integration over the whole thing disappears. Okay, so these terms disappear by symmetry. So the p times these guys is 0 integral d3p by symmetry. Okay. Symmetry of p goes to minus p. Or put otherwise, when this is a positive quantity and when this is a negative quantity, you get equal contributions because this is symmetric, so they cancel. The end answer then comes out to be integral d3p over 2 pi cubed p a dagger of p a of p there's a last step here also here. If I write this in the normal ordered, the regular form, a dagger a, so I convert that. I use also that what's left over is integral d3p over p, which is, of course, is also equal to 0. It's again, it's an odd function. Okay, so the momentum operator then, P on a state P1 gives me, it's the integral d3p over 2 pi cubed p a dagger of p, a of p, a dagger of p1 acting on that empty state. This thing is the number operator. It just gives me 1 back, or the other way we calculate it is we write this as a commuted with a dagger plus a dagger a, where this term gives me 0 and this term gives me a delta function. In either case, I end up back with the momentum eigenvalue and the same state again. Okay, so this is the momentum. So one of the lessons here is that what we had previously called pi, the canonical momentum, has nothing to do with the momentum. This is the momentum operator. We have it here. It's this guy. We have the Hamiltonian and the momentum density there. So just turning the crank on Lagrangian mechanics, we get these identifications, and they work out beautifully in the quantum version also. They give you the typical interpretation that the momentum acting on the state of definite momentum gives you the eigenvalue back, etc. So these are the quanta. Okay. Questions, comments? All right. Everybody finished copying? All right. Here's where I have to get rid of H bars and C's. So enough. Okay. There's many reasons for getting rid of H bars and C's. So I'm going to go to H bar equals to C equals to 1 units. And one is because the best reason is that it allows you to see the important stuff. Always putting these guys in only clutters the space up. It also lets you read all the books, which all do this. And okay, just quickly to review the transition. The first thing, if I said C is equal to 1, you can just think of this as measuring time in years and position in light years. Okay, so that things that like C times T and X turn into just T and X. They carry the same units. Okay. The consequence of this one is also that the energy, which normally in relativity goes like P squared C squared plus M squared C to the 4th, just turns into square root of P squared plus M squared. So at this stage, there's two basic units, T and X, and E, P, and M. So at this stage, there are separate units for years and energy. But if you also take H bar is equal to 1, then you know that since delta E, delta T is greater than H bar, that's going to now turn into 1. So the units of delta T are 1 over energy units. The units of delta X go like 1 over momentum units, delta P, which is the same. Those are the same units. P and X and T have the same units. P and E have the same units because I've already got C is equal to 1. If I do, the most important thing that I have is e to the I et minus P dot X over H bar goes to e to the I et minus P dot X. And those guys is now dimensionless by what we just did. That's good. And for future stuff, we haven't added the charge in yet. We're going to use E and M in the end. We're going to use Heaviside Lorentz. I'll review this when we get there, but alpha, the fine structure constant, which is 1 over 137, is in this unit is E squared over 4 pi h bar c. Well, of course, just then transfer into E squared over 4 pi. So the fine structure constant is E squared over 4 pi in these units. Okay, and the conversion factors, if you want to go back, it's pretty easy. Basically, h bar c, which is 1 in these units, of course, is, you can get it, is 197 MeV Fermi, or it's 1970 EV angstroms if you are doing things at the atomic scale. So if you're doing things at nuclear and particle physics, you tend to use the first one. If you're doing atomic physics, you use the latter. And C of course is 3 times 10 to the 8 meters per second. And this lets you get back all the units you need: energy, distance, and time come back with these units. And if you need electric charge, you go through alpha. Alpha is 137, multiplies by h bar c, and that's it. Okay. Okay. We'll also, when needed, we'll also use 4 vectors, so let's just do them again. Many of you have seen this, and if people that haven't seen it need more of a tutorial that I'm giving you, you can come and talk to me about it. But we're going to use x mu is, normally it's ct and x. Of course, that turns into just t and x right now. They'll be tied together. The derivative for vector is normally 1 over c d by dt minus del, minus the gradient. Bang, there's a minus sign there. That goes over then to just d by dt minus del, or sometimes we'll write it as d0 minus del. So mu equals 0 implies the time component. Okay, the momentum for vector is normally that. Of course, now just turns into E and P. Okay. When we form invariants, we use one lower, one upper. Okay, so this is the convention. Implication of that is that there's a minus sign in the spatial part. So P mu is E squared minus p squared by that convention, which is the mass, since E squared is p squared plus m squared. So p mu gives you the mass. And if I write p mu x mu, that's E times T minus P dot X. This is used so often that I almost always will abbreviate it as P dot X with no vector signs. Okay. So that if I write a plane wave, I write e to the minus I P dot X, no vector signs. That's e to the minus I E T minus P vector dot X. Which if we had put h bars in there, there'd be 1 over an h bar. Okay. For our string problem, we would, if we tried to adopt this notation for string problem, we'd write this as 1 over v d by dt minus d by dx, so that the wave equation, I can't remember, the Lagrangian was 1/2 1 over v squared phi dot squared minus 1/2 del phi, d by dx. This is our string, one-dimensional string. That squared, that was our Lagrangian. In this relativistic notation, then, this is 1/2 d mu phi d mu phi. And we're going to see that it's just the first component is so again, it's 1/2 1 over v d phi dt squared minus d phi dx squared. The equations of motion were were 1 over v squared second derivative with respect to t squared minus d by dx squared on phi, which in this notation is d mu on phi, which is abbreviated box phi. Okay, so there's the string in this compact notation. And lastly, integration. We have integral dt d3x when we integrate over all space and all time. That's then the integral d4x is the definition of that. This is a relativistic invariant. And the math way that you prove that is you do a Lorentz transformation from x and t to x prime and t prime, calculate the Jacobian, and it turns out to be 1. Okay, the physically length contraction and time dilation cancel each other, so the time dilation, time stretching, and length contracting along the direction of motion, the t and the dz along the direction of motion cancel each other. But math-wise, you calculate the Jacobian of the transformation. Okay. So the action principle okay. So previously we had the action is the integral dt d3x of this Lagrangian density, which is a function of phi d0 phi del phi. This still is true, and so sometimes we're going to have non-relativistic field theories. It's perfectly good to have a non-relativistic field theory. There's nothing about relativity that's required for field theory. But in a relativistic field theory, and so the previous formula still is the same, that the first integral is always can be written as d4x without, there's nothing there. But in a relativistic theory, the fields will depend on phi, and it will always be a relativistic invariant d mu phi. So whereas a non-relativistic theory can have d0 and gradient entering differently, a relativistic theory always has them entering in an invariant fashion. Okay. The equations of motion that we wrote before, if I take what was d by dt, dl, d phi dot, plus del dl d del phi minus dl d phi equaling 0. Okay. In our relativistic notation, this is d0 dl d0 phi. So the time derivative is d0. The gradient, we can keep the same notation if we want, del dl d del phi. Okay. In our compact notation, this turns into d mu dl d mu phi minus dl d phi. Okay. Okay, and that's what this means. This here, d by d0, d by dx, this is what that means. So these are exactly equivalent. I haven't really changed anything. Let me do the example for the string. The Lagrange density of the string we just saw was 1/2 d mu phi d mu phi. Then the variation of the Lagrangian with respect to d mu phi is d mu phi. Okay, I've got two d mu phi's there. And then the equations of motion say that I have d mu phi equals 0, which was the equation of motion that we had. Okay. So that's how you do this in a flash. Now, people that are new to the notation struggle a lot between uppers and lowers. Just so you know, here there was really one upper, one lower. But when I said that the variation with respect to d mu phi was d mu phi, there was a factor of 2 because they're the same thing. Okay. Which one I write lower and which one I write upper doesn't make any difference. So you can do a first approximation, just forget that one's upper, one lower, and then at the end of the day, just write everything in a relativistic invariant combination. That will work all the time. All right. So as we go through this, if you're struggling on that part, ask me. Okay, because some people are at this stage fluent in it and others aren't. Okay. Anyway, let me, just given the time, I'm going to not do some science, I'm going to just do dimensional analysis in this. In my last few minutes, I just want to do dimensional analysis. The Hamiltonian, we know, has dimension of energy. And I'm going to use energy as my basic unit. So let's just call this, I'll just say E. Okay, that means whatever units I want to use for energy. Then time goes like 1 over E from our commutation rules. And the action, which is the integral dt of the Lagrangian, okay, the Lagrangian Hamiltonian and Lagrangian carry the same units, is dimensionless. So e to the 0, which is good since, well, that's certainly good. When I go to fields, I have the action is the integral dt d3x of a Lagrange density. So those guys go like 1 over energy to the 4th overall, because there's 4 of them. They all carry the same unit in this basis. So the Lagrangian goes like energy to the 4th power. We'll call this d is equal to 4. Okay, The Lagrange density for the cases that we did so far start off like 1 over 2 d phi dt. Let me write this out twice, so it's d phi dt, it's phi dot squared. D by dt, or any derivative, any d mu, goes like 1 over energy. No, I'm sorry, it goes like energy. Blah, blah, blah. T goes like 1 over energy. D by dt then goes like energy. Okay? And if you think about this, if you think of d mu on e to the minus I p dot x, that turns into minus I p mu e to the minus p dot x, because I just bring down a derivative anytime I take that, a p every time I take that derivative. Derivatives go like p. Okay. So one of the rules then is any derivative that you have goes like an energy to the first power. And we see from what we had there that since the Lagrange density goes like e to the fourth, d by dt goes like e, that phi has to go like the energy to the first power also. Okay, pi was derivative of Lagrange in respect to phi dot. That then turns into something that goes like energy squared. Oops. And phi with pi is I delta 3 of x minus x prime. A delta 3 carries units of 1 over x cubed, right? Because d3x times delta 3 is 1. So delta of some variable carries the units of 1 over that variable. So this goes like 1 over energy cubed. So it goes like 1 over x cubed, which is energy cubed. And that works out because phi was energy to the 1, pi was energy squared, so you get energy cubed. Okay, so it's a little premature, but since I was just doing units, let's do it here. Later on, counting these dimensions tells you information about the dimensions of coupling constants. It will tell you whether a theory is renormalizable or non-renormalizable. So we're going to end up using this. The basic ones, the ones that I'm most interested in here, are those guys. All right. Good. So let's quit there. Next time I come back and we're going to talk about, we're going to start the introducing the field section. We're going to go through, what we've seen is the scalar field. I'll say a bit more about scalar fields, and we'll do complex scalars, vectors, fermions, blah, 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 the rest of the stuff. Okay, good. See you next time.